We'll go ahead and get started with the 12 o'clock session here. My name is Ben Shelton. I work with the North Carolina Center for Geographic Information and Analysis, CGIA. I will be the moderator for this session. We are here for the session titled Quick Methods for Recreating a DEM when Reprojecting a LiDAR Point Cloud, with presenters Doug Newcomb and Stephen Mather. I'll let them introduce themselves here in a second, but I'll go over just some quick notes, just some technical highlights here to know about this session. The chat on the right side of the screen will be available for any question and answers. So if you want to have a question during the presentation, go ahead and put your question there in chat. I'll monitor the chat and come back in about 10 minutes after the presentation, or 10 minutes until the session's over, and we'll have about 10 minutes for Q&A at the end. Just for a note that this presentation and all presentations for this conference will be available on YouTube after the conference is over. So keep an eye out for those communications and the NCGIS YouTube channel. So with that, I will turn it over to Doug and Stephen.
Hi, I'm Doug Newcomb, and for this presentation, I'm just a guy who likes to do GIS at home and play with point clouds. There's no connection between me and any federal agency for the purposes of this presentation. And Stephen?
Hi, Stephen Mather. I'm the GIS manager at Cleveland Metro Parks in Cleveland, Ohio. Got a little snow out the window today, and I can't find my cross-country ski boots, so I'm a little sad, but I'm glad to be here and presenting on some of the things that Doug and I have been talking about. Most of it's him and some cool things he's doing with DEMs, but I'll follow on at the end with some interesting stuff as well.
All right, let's get going. Why do you want to do this? Well, reprojection of a standard DEM can change the DEM values somewhat, and then you can also change your resolution in the method of creation to better match the layers that you're trying to match the DEM up against. The other thing is sometimes the official DEM can have some weirdness in it, for the lakes especially. For example, this is Roanoke Rapids in North Carolina. If you look at the upper end of the official DEM, you see all these triangles in here. It's not really a flat surface. Now, the problems with recreating DEM, if you just do inverse distance weighting, it's okay for small gaps and near the edges of holes, but the uncertainty grows as you go into the middle. And you end up with a ridge or a pit in the center, and you need flat water bodies and building foundations. Now, some of the challenges, if you're going to redo the DEM, if you do vector methods, they're great for small areas, but if you're doing a landscape level area, it takes a lot of memory. It can be kind of slow. And you need vector break lines for all those gaps if you want to force flatness on the surface. So let's look at a fully raster method. Well, the raster approach is you start out with a mean value of the ground points for every raster cell. You do a limited IDW interpolation to fill the small gaps and do a little strip inward on the large gaps. And then you go back and extract a strip of elevations for your shoreline, and you get the stats to the Z values on the shoreline, and then you apply a single value from those stats to the gaps. And then you can also use those stats to identify the areas where your approximation is going to be a problem. So folks, just think about this. I get my mouse up here as a cookie cutter. You're getting the shoreline here, and you're going to take a value from the shoreline and apply it across the entire inside. So starting with the ground points, it really doesn't matter what you use software-wise to get the initial raster, as long as it gives you a mean Z value and leaves no data holes. So GRASS, Poodle, Esri, whatever. I use GRASS GIS because I can throw thousands of tiles at it in one time and process it as a single unit. Doing the mean value moderates your outliers in each one of these cells. This is in Virginia Beach County, and you can see where I've gone through and done a 1 meter example of this, doing the mean value. You can see the holes where you've got it for an artificial pond, you've got it for building foundations, you've got it in a swampy forest, and then you've also got it for a natural water body. This is a 7/10 meter posting with a 19 centimeter vertical accuracy. So we do a partial IDW interpolation using GRASS RFIL stats. You want to make sure when you're doing this that you have a mask over the area that you're doing so that the outside is not incorporated into any processing. So what you do is the R field stats with a K input in the mean raster grid and your output cells. How many cells do you want to go in? Well, if I'm doing a 1 meter resolution grid, I'll go in 5 cells. If I do a 3 meter, if I do a 5 foot resolution, I'll go in 3 cells. 15, 16 feet is about my comfort level with interpolating into the gaps. The K flag on there keeps the original values in the input raster so that you're not processing those, you're just processing the gaps based on the original values. And that speeds up your processing with memory and requirements and just general speed and so this is what it looks like once you've done that initial IDW interpolation. You'll see a lot of gaps, but a lot of the smaller areas have been filled in. Now, with the next step is that we want to convert those nulls into a value of 30,000 or more using R null in this case. Why 30,000? Because Mount Everest is 29,000 feet above sea level, and that'll cover everything. So it'll be different than anything on the surface of the earth. All right, so we want to then divide everything in that raster by 30,000 and convert it to an integer. That makes a 1-0 grid. You get rid of the zeros, so you now have a 1 and null grid. So then you want to buffer outward back to the original shoreline. Remember, we came inward, in this case, 5 cells. So we want to go back out to create a raster buffer going back out to the initial area. So this is what the null areas would look like in the 1 and null. And then we buffer each one of those so that you've got a zoned buffer. And you select the ring of that zoned buffer that overlies the original shoreline of a water body. Then you can use a mask and then select the IDW interpolated values using that strip mask, and you end up with a ring around every footprint of the building and every water body. Now you go back to your buffer and you make it, instead of a zone buffer, you make it all one value, and then you run a clumping routine on it to give each clump a unique value. So now you have zones where each zone covers a strip around every water body or building footprint. So then we run R univar on the strip raster layer and use the clump raster as a zone raster on top of that, so that the Z-stats for each shoreline are calculated separately for each zone. And it spits it out to a comma separated value file. It doesn't take long for this one, it took about 3.5 minutes. Got a thing that you have to remember about your statistics is you got to get them that are resistant to the influence of outliers. LiDAR points can do funny things on the edge of water. And the minimum value, that can be misleading. So your first quartile seems to be, at least at my first cut at this, the first quartile is more resistant to the outliers and seems to give me a pretty good value. The standard deviation gives me an idea of shoreline variability. Because the one thing this doesn't work too well on is double line drainages. I'll have to come up with something different than that. But using that Z standard deviation, I could computationally identify those areas for later treatment. So now let's look at the statistics. When you get this CSV file, I'll pull it up in a spreadsheet, but you got to remember, folks, spreadsheets only go to about 1.5 million values. If you're going to do large areas, you're going to have to do Python or something similar. So here's the zone value, zone 1, the minimum there, the standard deviation, and the first quartile. You go to take that text file and you convert it to another text file, which has the zone number equal to 100 times the first quartile value. So you're converting that to an integer and doing the reclass routine in GRASS. You can then convert a raster from zones into the integer elevation values. And you can also do the same thing, creating a standard deviation value. And in this case, I'm saying everything less than a foot's 1, 1 to 2 feet, 2, 2 to 3 feet, 3, so on, so that you can see how much of a standard deviation is for everything. In this case, you can see now almost everything's a good value. You've got some areas that are got a low difference, and then you've got these other areas which are actually riverine coastal systems draining into the Chesapeake Bay in this case. And those are areas that are going to have to be treated differently. So you trim the new rasters to the actual extent of the water surface. So you just go use your buffer layer again to go just inside the shoreline, convert those rasters that you've created to floating point, divide by 100. Then you use those rasters to cut holes in the original interpolated fill raster, and then you merge them both together and you've got a final surface. So why not just reproject the break lines? Well, you don't have break lines everywhere. It doesn't happen for buildings, and your water bodies have to be over a certain size before you can do that. You can see in the upper right here where it's just the break lines, and then lower left, you've got everything that was processed in this county. Standard break lines, as I said, they only get certain sizes of water bodies. These are the gray are the break lines for this area. And then you see other water bodies and buildings that are outlined using the other method and ready for processing. So if we compare the two, if you look at the DEM for the elevation, there's very minimal difference between the land surfaces, but there's significant difference here between the water level surfaces, up to 4.5 feet on this one up here. So let's go down to see, which one's right? Well, if you look at the Back Bay estuary, which is part of that, the break line for the shoreline on this is 3.5 feet below NBD 88, 0. Whereas the edge strip value I'm getting for this is 0.196. The closest gauge for that is tens of miles away south in Corolla. And you can see here that at the day that LiDAR data was flown, that it's much closer to what the strip method has than the break line. And in the interior pond on that island right there has an even deeper hole from the break line than has outside. Okay, on to the next. Here in North Carolina, here's another example, Hyco Lake. You've got the gauge height. It's got the break line water level is 49.14. Raster Approach, the strip method is 410. And you can see that the gauge height, in this case, when we do the conversion to NVD8 from what the gauge height is in NG29, it's actually a split difference, but the kind of uncertain about what the accuracy is of the conversion. So that's kind of splits our difference on that one. But if we go down to Lake Mattamuskeet, which has 2 gauges, one on the west and one on the east, on the break lines on the west have it -0.5 feet. The break line on the east have it -0.7. The raster interpolation gives you 0.35 on the west and 0.31 on the east. And if you look at the gauge heights, you have to subtract 2 because they're so close to the coast, they add 2 to all the gauges. You can see that the raster interpolation is within the accuracy band of the LiDAR itself. So I personally am very confident about this method. It may need some tweaking though. It's good enough for vegetative analysis. I just sort of stumbled into this for the water bodies. It's a very fast method for hydro flattening, and it does a more complete job for smaller water bodies across the landscape. I think it's as good as the other methods over the past 10 years for the ponded water bodies, not the double line. Double line drainages are going to need some work. One thing I would like to do is the quartiles for the next best step. We need to go to maybe decile, 15 percentile, 20 percentile, and see if there's something that works a little better. All right, Stephen, it's all yours.
Awesome. Thanks, Doug.
No problem.
This has been great. So, anybody who knows Doug, it's probably seen portions of this before and where it's coming from and where it's going to. And I'm really excited about the double line work and where that's going. But I can't believe how good the hydro flattening is for water bodies. It's just awesome, and especially the scalability. Like that's fantastic. So I'm going to talk about something that's not nearly as scalable because it's actually largely vector techniques. A second to find my let's see, There we go. So I'm going to talk a little bit about filling gaps in city elevation models, and we're going to go a little bit to a right angle from LiDAR and talk a little bit about photogrammetric data sets, which share characteristics, but also have some significant differences. So specifically, we're looking at photogrammetric data sets over Zanzibar and Tanzania. The Zanzibar Mapping Initiative is the largest area surveyed by low-cost drones in the world. It's fantastic, and I think it highlights some opportunities that we have. LiDAR is still the gold standard, but highlights some of the opportunities we have with respect to photogrammetric surveys, allowing us to do things that we might not be able to do with just LiDAR. So for example, either flying elevation models in low-cost environments where LiDAR might not be sustainable, or filling in time series between LiDAR flights with photogrammetric data. I will highlight, I won't talk much about this in the presentation, but the data flown for Zanzibar Mapping Initiative was optimized for orthophoto creation. So this, as such, is a really challenging data set for getting elevation models out of. I co-founded Open Drone Map a few years back. It's become kind of a pretty useful tool for projects like this. I'm not going to talk about that today, but that's what feeds the data in. And when we get to the, what's that?
Your slides are not advancing.
Oh, that's a problem. Why don't we switch back to you, Doug? And,
okay, I'll do that. Oh, you got to unshare. Okay.
Yep.
Let me share my screen. Okay. And let me share from this one. Crap. Well, all right. I said current slide. Apparently it didn't leave me. So let me get down here. Okay. There you go. Just tell me when.
Oh, I see. Perfect. Hold up 1 second. I can't see your screen. Oh, what a dance.
I don't think you're sharing. I don't see slides.
You don't see slides. Okay, hold on a second. I thought I shared it. Desktop 2 and share. Okay.
There it is.
There it is. Okay. So let me get that slideshow start from the current slide. Yeah. There we go. We're on Open Drone Map. Okay.
All right. All right. Next slide.
Okay.
So there are a lot of great algorithms in the wild for filtering LiDAR data, whether, using, and those include things from Zhang, Bartels, and Pingel. And we often sort of, as a shortcut, use these LiDAR filtering algorithms with photogrammetric data because they're convenient, they're well documented, they're predictable. So a lot of times we'll use morphological filters. We could also use cloth simulation or skewness balancing. But these are really optimized for true three-dimensional data sets. And depending on how a photogrammetry data set is flown, they may not be truly 3D in the sense that LiDAR is. So not penetrating, not getting multiple returns, not getting in between all the spaces. So with this we've played around a little bit with an alternative. So our geomorphon is a great little landscape classification algorithm that has that it really takes the state of the art for landscape classification up. And I won't get into the details of this, but one of the advantages it has is that it's not just a distance-based filter, but actually uses line of sight. And I was curious whether it would be useful for filtering other 2.5D information, specifically for helping us filter the Zanzibar data. Next. So here's the data that we're going to filter. It's a building foot. We can sort of see the signal of the overall landscape behind. We can see the stream flowing through, the drainage flowing through the middle. We can see some high areas, and we can see the building footprints. Next. So if we run geomorphon on this, the results are actually surprisingly good. We get those low-lying areas showing up as valleys and depressions. We get the roof lines showing up largely as a range of higher values. And this, for a completely automated technique where I twisted one knob, is very, very promising. Next. So if we compare this to building footprints, and if we just pull out just those low areas, we see that it captures areas in the narrow alleyways between buildings very well. It captures those low-lying areas of the stream, and it captures the larger areas pretty well as well. Next. Comparing this then to building footprints, it compares quite favorably. It even captures these sort of relatively typical courtyards in between the buildings, which we might ultimately want to filter out. But it's quite detailed and does a really nice job capturing landscape features that even manually we probably wouldn't digitize. Since we have for this data set a building footprints digitized, we're going to cheat a little bit. And we're going to use a small buffer around those buildings to filter out additional data. And then we have the opportunity to, then we have to figure out how are we putting all this data back together. And actually, parts of this project are going to take advantage, I think, of Doug's approach. But I wanted to look at what are the possibilities of interpolating between those buildings in the small alleyways. So I used vsurf ICW, which is an inverse cost distance. So if you're familiar with inverse distance weighting, this is the cost version of that, which means we can include hard or soft costs along the edges of it. This is the example from the documentation in GRASS. In this case, we use the buildings themselves as a hard barrier and use vegetation. We could potentially use vegetation as a soft barrier. Next. So what kind of results do we get from this? We've got two algorithms and one additional data set. We basically just perform our landscape classification, filter with additional information, feed that into ICW, and we get these wonderful this wonderful landscape that accepts out those buildings and doesn't treat them as a hydrologic surface. So this is a short area. This is presumably the easy area in Zanzibar City. If we go to Stone Town next, where we've got 4- and 5-story buildings with the same kinds of densities, we see a really sort of a nice pattern that looks like the landscape actually does. I've walked these streets, I've been in these places, and this is in fact the shape of, this is very close to the shape of the land underfoot, which is really promising for doing hydrologic analyses over these large areas. Unfortunately, unlike Doug's approach, this is not pure raster. So the next step is to chunk this into pieces and make it run on lots of cores. And I think we're on to questions.
Yep, questions.
All right. So far, the only question was if we were looking at the correct screen, and I think we fixed that. Sorry for the technical difficulties. So going back to the LiDAR that the DEM is created from, does it matter the quality of LiDAR, like QL2 or anything like that? What type of data did you all use or derive these from?
Mine was QL2, not quite QL2. I don't think the Virginia data has the vertical resolution accuracy to meet QL2, but it had the horizontal accuracy for the point density. And I think that's the important thing, is that you need to have something that's going to have at least 1 point for every square, maybe more. Most of the LiDAR data being flown these days is QL2. I did find some data back in Alabama, or I think it's Mississippi or Alabama, that on the web that I may be able to process it is probably QL3, QL4, and I'll see how that works, at what resolution works best with that, to see how robust the technique is. I don't think with the current densities we have of LiDAR, it's the tinning methods are great when you have sparse data, but right now we've got very dense data, more dense than we're probably going to be used at the resolution we're doing analysis. So I don't think that tinning actually will give you a much better ground surface.
Okay.
So really the tinning then, Doug, is like, that's a legacy that we should be reconsidering.
Yeah. I mean, the tension splines were good too for sparse data, but like I said, if we've got all this data, why not just, and we're not going to go down to the quarter meter, then we're just looking at a meter, then we should be able to just average the points and go from there.
Okay, great. So what type of coverage have you run this on it, like size wise, square miles or things like that? Is there a limit that you've hit, or have you just kind of only been interested in certain areas?
Well, in my day job, I've merged together all the phase 1 and phase 2 LiDAR for the coast of North Carolina into a single virtual raster, linked that into GRASS, and then ran this process on that in one shot. It took about 3 hours to do the IDW interpolation, and every other step took about another half an hour or so for like the clustering. Maybe, clustering I think took an hour, that's right. But that's a 55 billion pixel raster. And I was able to do that on my laptop.
Wow.
With, I think it only used about 5 gig of RAM and I think most of that was when I was writing out the end product geotiffs. So
wow.
it scales very well.
That's pretty impressive.
Yeah, and I really do. I've got some ideas about coming back and doing raster methods for doing the double line drainages. And the other thing you have to watch out for is where you have an impoundment that has a double line drainage flowing into it. I can't see any way around putting in a break line that goes into the raster to clip, so you can cut between the clusters, make 2 clusters instead of 1 for that, so that you're processing the lake separately from the double line.
But you've already eliminated so many other manual inputs. That seems like barely a nuisance.
There's a lot of comments in the chat that you probably, if you don't have the attendee hub up yourselves, I'll pass along. Brady Walker has said that it's a great presentation. Patrick Williams said nice work. So a lot of good encouragement. Patrick Williams also said, always enjoy seeing GRASS 3D visualizations.
Yes, right. That's what this is. That's HiCo Lake.
Daniel Rosenbaum, this is awesome. I'm looking forward to returning to experiment with this. And Michelle Babson said thank you. So everybody's participating and enjoyed the presentation. You guys must have done a great job. No questions.
All right.
All right.
That's rare.
So everybody, I just want to say thank you for attending another great session. And I guess we have a little bit of a break here at 12:30 with the agenda showing, I believe the next session's starting at 1:30. There is a vendor demo starting at 1, so I invite everybody to attend that. But otherwise, thanks guys. Thanks, Stephen. Thanks, Doug.